Yeah, thank you very much for the invitation. So I think I mean, I'm happy to share a little bit of what I have been working with and what I'm working with currently. So the title of the talk is Improving Security Testing Using Dynamic Program Analysis. So I wanted to start with a little bit of sort of introduction like that. I hope you can see the slides. Now.
Oh, we just lost them.
Oh, that's too bad. Let me see. Okay, let me try again. Okay, now.
Perfect.
Okay, great. Yeah, so I got my PhD in 2019, and I'm currently doing a postdoc at the Department of Computer and Information Science at LiU. So my research broadly are within the scope of system security, so this sort of securing hardware and operating systems and system software from a sort of technical perspective. And the reason for my interest in this particular area are the sort of countless examples of supposedly well-designed systems where the security turned out to be completely undermined by some minor implementation mistake. So I think, I mean, from my point of view, it's very important to be willing to sort of dig into the gory technical details when you're dealing with security, because the devil very much is in the technical details. And within this sort of general scope of system security, my particular interest is in software security. So here I've been working in I would say 3 main fields. So sort of low-level program analysis, machine code and bytecode analysis. This was the topic of my PhD. Lately, I've also been doing some work on malware defense and the closely related area of obfuscation. So malware authors usually use obfuscation techniques to make life harder for the defenders. So I've been doing some work on Android malware, looking into what kind of obfuscation techniques are used, and I've also been looking at some obfuscation techniques used by PC malware, for example. But the third main research interest of mine is security testing, which will be the main topic of the talk today. And in particular, a technique called fuzzing or fuzz testing. So a little bit of background on fuzzing before we get into the main content of this presentation, which will be a little bit of a discussion of some previous work that we have done and also some ongoing research projects. So fuzzing or fuzz testing has become one of the most popular security testing techniques today. It's very widely used in industry, and consequently also there's been a large interest in academia lately. Many of these sort of secure development standards or principles actually mandate fuzzing today. So the idea is conceptually simple. So you send some kind of semi-random data to programs to test if they are robust against malformed inputs, or if they will crash or misbehave in some way. And this has proven, even though conceptually simple, it has proven very effective at finding these sort of low-level implementation level security bugs that can often be exploited for arbitrary code execution. So they potentially allow completely taking over a computer system. So these sort of native code memory errors like buffer overflows and use after free and so on, this is where fuzzing really shines. But we also have fuzzing for higher level code like web applications and so on. So it's a relatively broad category of automated security testing techniques, but they all share this idea of having some kind of semi-random input generation. There are a couple of different approaches to fuzzing that have emerged over years. So the very early ones in the early 2000s were black box fuzzers. So they treated the program under test as a black box without any kind of feedback or analysis of the program. So essentially just generated some input and then checked if the program crashed, basically. So here we have two under categories, the mutational fuzzers that are the simplest ones that just generate inputs by mutating a set of well-formed so-called seed inputs, which have the benefit of being simple to start with and requiring very relatively little work to sort of begin the fuzzing, and also being very fast, because the test generation is very computationally sort of cheap. The downside is that the code coverage is very poor typically, because you tend to break the input so much that it's rejected very early by sanity checks. And so generational fuzzers was a kind of response to this, that essentially used some kind of input specification, a grammar or something, to generate inputs. And this has much better code coverage, but on the other hand, it takes a lot of time to actually create this input specification. And so a little bit later, somewhere like 10 years ago, there was a lot of work on trying to use symbolic or concolic execution for automated test generation. So you record some pause constraint for the program, and then you use a constraint solver, an SMT solver, to generate new inputs. And this is conceptually a very nice idea, so you can get past very complex constraints on the input, and which would be very hard to do using random input generation. But there are also some serious scalability problems here, because SMT solving is an NP-complete problem. So scalability has always been a very significant challenge with the so-called white box fuzzers, because the analysis is very expensive, very heavyweight. So it never really caught on, even though a lot of work was spent on trying to make it more practical. And instead, what we got, which has become the sort of de facto approach for fuzzing use today, is gray box fuzzing, which essentially is mutational fuzzing with coverage feedback. So in a mutational fuzzer, you have this input corpus, the seed inputs. I can turn on this laser pointer so we see a bit better. So we have this set of so-called seed inputs. The fuzzer take those and apply some random mutations and send it to the program under test. And the black box fuzzer don't have any kind of insight in what happens in the program, so it just checks if the program crashes or not. And what essentially gray box fuzzing conceptually does is that it just adds a feedback loop. So we now measure the code coverage also, and if mutated input triggered some new code coverage, then that input is saved in this set of inputs, in seed inputs. And so the fuzzer will sort of loop over them continuously and apply mutations. And this works as a kind of very simple evolutionary algorithm that allows the fuzzer to sort of gradually discover new paths in the code and figure out how to solve constraints on the input. And this seems to hit some kind of sweet spot in between the very simplistic mutational black box fuzzer and the very, very complex white box ones. So it's much better at finding new code coverage than the black box fuzzing, but it's also much more scalable than the white box. And this, for many programs, this sweet spot is actually better than the white box fuzzing, that it somehow the improved scalability actually compensates for the lack of advanced constraint solving abilities. So this is really what has become the sort of standard approach to fuzzing today. So I'll get back a little bit to that soon. First, I wanted to mention a little bit about two previous works we've done on fuzzing. So one called Mutations, where we essentially turn an existing binary into a generational fuzzer, and the second one that we call focused fuzzing, which is about gray box fuzzing, and in particular to sort of focus the mutations on the most quote-unquote interesting parts of an input to speed up the process. So the mutagen system is a black box fuzzer. It's a little bit hard to fit into any one of these categories. But the idea is to somehow marry the benefits of the mutational and generational fuzzers. So the low kind of effort in setting up the fuzzer for mutational fuzzing with a better code coverage of a generational one. So like I just mentioned, the mutational fuzzers essentially just introduce some noise into the input files and use that to generate test inputs. And this has the downside of typically destroying the structure of the input so that it's reacted by early sanity checks by the program under test and never really reach the deeper logic where bugs might reside. So the idea with this mutagen system is that we take an existing program that can generate valid inputs to the program under test. So if we, for example, want to test a PDF reader here, we have a program that can generate PDF files. In this example, a PostScript to PDF converter. And then we essentially inject bugs into this program so that when it generates PDFs, the PDFs are a little bit sort of screwed up. But since we're mutating the generating program rather than the input itself, these mutations will be on a somehow higher semantic level. So they're more likely to pass these sanity checks and therefore reach deeper levels of the code and find more bugs. And when we tested this, we actually saw that we got about an order of magnitude better code coverage and also found a number of bugs that were not found by previous fuzzers at the time. So to very briefly explain how it works, we perform dynamic data flow analysis on the generating program to find out instructions involved in generating the output. And then we use to dynamically modify this using a dynamic analysis framework. So the mutations are a little bit similar to mutation testing, if you heard about that. So essentially, we're injecting bugs into the program so that when it runs to create the output files, they are a little bit transformed in some way. That's a very brief introduction to the concept. So I will not go into the details here in the interest of time. So the second previous work I wanted to mention is this focused fuzzing idea. So here we also use dynamic data flow analysis to find out where each byte of an input to the program under test is used by the program, and then we use this to focus the mutations on the bytes that sort of touch the previously unseen part of the program, where the intuition is that these are the bytes that are most likely to trigger bugs or result in new code coverage. So we focus the fuzzing, the mutations of the input on the most important parts, so to speak. So we speed up the fuzzing process. So this is not likely to improve the sort of ability to find new bugs or expose new code coverage, but it sort of speeds up the process. So to a little bit better understand the intuition, we can look at an example. So we here have some kind of program to parse an input format. And it's some kind of binary input format where we have this relatively common idiom of having some kind of part of the input that states how the following part of the input should be interpreted. So in this case, we have something that has the type 10, and that says that the following byte should be interpreted as text data. And in this particular format, we can also have image data and maybe something else. So if we run this through a mutational fuzzer and the fuzzer at some point mutates this byte here to become 11 instead, that will cause the program to instead go down this path. And now it will try to interpret this, which was the text data in the original seed file, as an image data instead. And so in order to be able to continue exploring the program's ability to parse image data, what we need to do is essentially that the fuzzer needs to start transforming this text data here into an image data. So sort of discovering the appropriate format for this part of the input. In order to be able to do that, we really should be focusing the mutations on these 2 bytes here. So if we mutate anything here, then we will probably go down a completely different path and sort of abandon this new piece of the program that we just discovered, which will be sort of wasting time because we have probably already explored that part of the input space. So to maximize the likelihood of uncovering new code coverage or finding new bugs in this image parsing part of the code, we should focus on the 2 bytes here. And this is what this focused fuzzing does. So it will discover that this part of the program here is now, or these 2 bytes here are now being read by part of the code that we have never seen before. And so these should be the sort of focus bytes for this particular input. And again, we use some dynamic data flow analysis to achieve this. There are some trade-offs here, of course, that it incurs quite a bit of overhead to do this data flow tracing. So we can really only do this, the benefit is greatest when running the program under test is relatively slow, or when even the minimum input is relatively big, so to speak. So these were 2 previous works. I also wanted to say a little bit about some ongoing projects. So one of them is a sort of a project to generate fuzzer benchmark suites. And this is motivated by the lack of established benchmark suites for testing or evaluating fuzzers, which means that everyone tends to use their own benchmarks or their own benchmark methods. So it's hard to compare the performance of fuzzers, which of course hampers the development of new fuzzing techniques. There has lately been some development on this, but the existing works have a number of drawbacks. So the most sort of easy way to use this, or to do this kind of evaluation of fuzzers, is just use a set of old versions of programs with known bugs and then see if the fuzzer can rediscover those. The problem is that this requires manual crash deduplication. So typically fuzzers are very good at finding multiple ways to crash the program due to the same bug. So if we have the fuzzer finds 100 crashing inputs, we don't know if these are all due to the same bug or if it's 100 different bugs or anything in between. And in order to figure this out, we need to manually check each crashing input, which is very labor intensive. So some alternative approaches to trying to sort of generate some kind of ground truth to automate this crash deduplication has been proposed. One idea is to create buggy software with sort of manually created buggy software where we only have 1 bug per program. So the problem here is that this might not be representative of real bugs, and also we have a small number of bugs. Another idea is to inject synthetic bugs into real software, which is scalable, so we can generate a lot of bugs, but they might not be very representative again of real bugs. And the third approach is to manually reintroduce or backport old bugs into new versions of the program. So here we have sort of high quality bugs because they are real life bugs, but of course it takes a lot of work to actually do this backporting and maintain this benchmark suite and so on. So an example of this is a system called Magma that was published recently. So this approach is really the best one, but again we have the problem that we have a limitation in how many bugs we can actually reintroduce because it takes a lot of work. So what we want to do is to automate this process, and the input to our system is a Git repository of the software that we want to reintroduce bugs into, and the current stable commit of the latest version, and the set of bugs. So we have n bugs, where each bug is accompanied by the commit just prior to fixing it, and the input that triggers the bug. And we can get this from public bug trackers, like, for example, the Google OSS Fuzz system. And then the idea is to use techniques from automatic program repair to sort of minimize the diff between a buggy commit and this newest version of the software, so that the particular bug is kept, but the other changes are minimized. So we're using some genetic algorithms that are similar to the techniques used for automatic program repair. And then we can merge all these different versions. So we create one version of the program per bug, and then we can merge them into one version with all, or at least most of the bugs in one program. And that's what we actually use for testing the fuzzers. And then when we find a crashing input, we can run the input on each of these versions of the program to find out which of it that crashes. And this is a way to automatically determine which bug it was that we found. So it's a way to achieve automatic crash deduplication. So this is the idea. We have sort of the overall design for this system, and I have a master thesis student that works on implementing this. So we'll see how well it works. So this is ongoing work. Finally, I wanted to spend a little bit of time, and I don't have so much to say on this one because this is more in the planning stage, but we also have a planned project where we want to sort of more fundamentally understand why fuzzers work and what affects fuzzer performance. So previous work have mostly focused on developing new fuzzing techniques, for example, the ones that I mentioned that we have done ourselves. But it's also important to better understand the sort of fundamental properties of fuzzing. What is the main source of performance variation of different fuzzers on different programs, for example. So we see that two fuzzers that are conceptually very similar in their design can still have very significant differences in performance on different programs. Ideally, we would like to be able to predict fuzzer performance, so find a good proxy for the bug finding ability that we can easily measure. Like we know that certain code coverage measures are relatively well correlated with this, but there are also some limitations of this. So this is something we want to study, and also finding out what are the best sort of coverage metrics, or maybe finding some combination of coverage metrics or some new coverage metrics that are better at predicting how a fuzzer will perform in the general case. And the idea here is to run one of these benchmark suites, maybe the one we create ourselves, or this Magma system that I mentioned, to generate a lot of examples of running different fuzzers on different programs, and then analyze this to try to answer these questions. So this is a little bit more of an exploratory research project. Okay, so that was it. I will stop here so we have some time for questions. Yeah, I'll be happy to take questions.